So it's been a bitterly cold day when filming this, and I've had the fan heater on in the lab to try and warm the place up a little bit. And it's the motor in that got me thinking about making another video. Coincidentally, I've been teaching electromagnetism to my 5th form, and they need to know how motors work, but particularly the DC electric motor. So let's see if we can explain today how the DC electric motor works. And then all you do is just put your drink down on the bar and you leave it alone. I'm not sure you expected that to happen, and neither did I. So let's try and explain what's happening. Electric fields apply forces to charges. Why does putting two transparent things on top of each other do something so strange when you turn it through 90 degrees? So you might remember from a previous video of mine, we looked at Fleming's left-hand rule. We looked at forces on wires in magnetic fields. So a very quick recap here. If I take an electrical conductor and pass electricity through it, so I'm going to connect it to the positive of the power supply and this end to the negative, we've got electricity coming towards you. This is the north of the magnet and this is the south. So if we use Fleming's left-hand rule, we've got first finger field, there's the current, and the wire should be thrust upwards. So we need to understand this before we can explain how a DC motor works. So got the current that will be coming towards you, magnetic field going across at 90 degrees. We'll turn the power supply full up and turn on and see what happens. 3, 2, 1, go. And there you go, you see the wire is thrust upwards at 90 degrees. So, power supply just tripping out there because of the large current, and also the wire feels quite warm. That's another sign that there was a current flowing. But the important thing is we got some motion, and we got a wire moving upwards. Well, if you think about it, if we turn the direction of current round, and instead of having the wire coming towards you, have it in a coil coming away from you as well, that side, with the current flowing in the opposite direction, will be pushed downwards. And if you think about it, if one wire is forced upwards and the other wire forced downwards, we're somewhere near to getting rotation, which is what we need for a DC motor. Right, so we now know what we need to make a DC motor. So here's a little model that we made a while ago, and this is a fully working DC motor. Think of the things that it needs. It needs a magnetic field. And so these two magnets provide the magnetic field, and they must work across the coil that's in here. In other words, it must be north to south. You can't have a north pole facing a north pole on the other side. The next thing you need is some wire going through the magnetic field at 90 degrees and also through the magnetic field at 90 degrees in the opposite direction. So, using Fleming's left-hand rule, one set of wires will be pushed upwards, one set will be pushed downwards, and that, on a spindle, is what's going to cause this to rotate. But there are a few things we can do to make that rotation better, and we've got to solve the problem of, if this side is pushed upwards, how can we get it to be pushed downwards when it rotates through half a turn? So here we are with our DC motor. You remember the bits we need. We've got a magnetic field going across, wires in a coil going round and round. So one conductor set going this way and one going the other way. This one might be forced upwards if we connect it the right way around, and this side will be forced downwards. And the end of these coils are connected on either side of this shaft to what we call brushes. And the brushes touch on and they disconnect and reconnect and disconnect and reconnect on every half turn. So if I've got a positive wire here, it'll connect to this side and force this up, but then it'll disconnect from that side, and now these wires will be touching the negative and it'll be forced down. It's quite a complicated thing, and most students find it very difficult to understand. But the main thing is that the wires going in and out of the coils connect to the positive, get pushed up, connect to the negative, get pushed down, and as it rotates, there's that connect-disconnect, which changes the direction of current and therefore changes the direction of the force from up to down, and we get rotation. So we're just about there. Let me very quickly whiz through what we've got here. We've got a magnetic field at 90 degrees to a current. We've got some turns here. More correctly, it's one coil with lots of turns. And we've got two brushes, a positive and a negative one, acting on the rotor, onto the commutator of the rotor. And the only thing that's not so good about this little motor is to get a bigger force, we need a stronger magnetic field. So you would normally wind these turns onto a soft iron core. But for this one, a wooden one works fine. So let's connect it up and see it working. Right, so a couple of wires to the power supply, so in we go here. We'll just make this side negative. I haven't done Fleming's left-hand rule on this to see if it goes up or it goes down, but we'll find out soon. And we'll make the other brush always positive. So that will always push the wire on this side in the same direction. Turn on the power supply and hopefully it'll start straight away. So here we go, turn up the current. Now it's stalled there because the wires aren't in the magnetic field, but let's get them into the magnetic field and there we go. Okay, turn the current down, turn the current up. So we get a greater force, turn the current down again, and finally turn the current off, and it stops. It stopped in a very interesting position because it's worth pointing out that the wire has to be in the magnetic field, and if it's out here, it's actually trying to move in the same direction as the magnetic field, and it's also rather outside it as well, so that motor will never get started. You'll probably find actually the brushes aren't touching at that angle, they're only connecting here. So let's very quickly see if I was right. Turn the current, or at least turn the voltage up and turn on straight away, and it should go straight away. And we've got some power control or torque control on our motor by changing the current flowing through the coil. I just wanted to be a bit more specific about why the motor won't start from the vertical position, or why it can sometimes stall in that position like it did a bit earlier on. If you remember, Fleming's left-hand rule has everything at 90 degrees. The magnetic field goes across, the current goes at 90 degrees to the magnetic field, and the force is felt on the rotor either up or down. So when the rotor's in this position, regardless of any other reason, we've got the magnetic field going across, that's fine. We've got the current going at 90 degrees, that's fine. But the force to be at 90 degrees on the rotor must be up or down. And of course that would have the effect of lifting or pushing the rotor downwards. So it's just not going to rotate when it's at this angle. So you might ask, well, how does it manage to keep going round and round then if there's no rotational force on it here? Well, once it's got going, its momentum carries it past that point, and then it can feel a force, a component of force getting ever larger vertically, and that can cause the rotor to keep rotating. So just before we finish, here's a rotor out of an electric drill. This is the real thing, not a model. The stator, the case stays where it is. I hope you can see all the relevant bits. You can see the soft iron core, lots and lots of turns, and in fact there are different coils at different angles to stop it from stalling. Here's where the brushes touch on the commutator. The brushes will be in the case, and it's mounted on bearings so it can freely rotate. And why I brought this out partly was to show you, I don't know if you can see it on the camera, but there are some bits of metal missing from the heavy rotor. That should be the subject of another video really. That's because you'll notice this shaking because it wasn't totally balanced on either side. One side's heavier than the other, so they cut out bits of metal where the rotor is a little bit too heavy to make both sides the same mass, and if that's the case, it won't shake a lot when you use it. It's dynamically balanced. Excellent. Well, I hope you enjoyed that video and learnt a little bit more about how electric motors work. They're quite complicated devices, but if you get part of the idea, you're on your way to understanding it fully. So, do hope you enjoyed that, and I look forward to seeing you again next time.